Hello, everyone. Welcome to today's class. Today, we will continue to talk about R basics, and we will focus on R programming today. We're supposed to use 2 lectures to talk about R programming, but we only have 1 lecture of time. So I'll try to talk about everything, but if we cannot finish, you can read the slides by yourself after the class. I think everything is very clear, very straightforward. I think you should be able to learn the rest of the materials by yourself. Okay. And as you can see, homework 1 does not include anything about R programming, so it should be good. All right, let's start. There are 5 topics in this part: condition and control flow, loops, functions, and apply family of functions, and best practices in coding. So the last part is particularly important for beginners in programming, no matter what language you are using. So these are common best practices in coding. All right, let's start. So first, conditional execution, the if statement. Take a look at the basic conditional construction in R. So the syntax is if parentheses some condition and action 1, else action 2. Okay. So this condition is a conditional expression that would return a true or false value. So it will return a logical value. And if it is true, then action 1 will be executed. Otherwise, action 2 will be executed. Only 2 scenarios. And in case that the program does nothing if the condition is false, then you don't need to use the else statement. Okay, only the if part is sufficient. Okay. If you don't want to do anything, if the condition is false, then you can omit this part. Take a look at an example. X is equal to -5. And then I write a conditional flow. If x is greater than or equal to 0, y is equal to x, else y is equal to -x. So y is actually the absolute value of x. So you use the if statement to create a new variable called y. And because x is negative, right, the condition is false. So this action 2 is executed. So y is equal to -x, which is negative of -5, which is 5. So very simple. This is a if-else statement. Right? And there is a warning, an important thing about the if statement in R. So the condition can only test a single element, not a vector of elements, which means the condition can only accept a single logical value, 1 true or false value. It cannot take a vector of logical values. So for example, take a look at the following code. X is a vector, 1, 2, 3, 4, 5. Then if you put this expression in the condition part, x is less than 3, we know that R does everything element-wise. So x is less than 3. This conditional expression will yield a vector of 5 true or false values, right? If you do that, you see, you will get an error message. So the condition has length greater than 1. So the condition can only has length 1. If it is greater than 1, then you have an error message. So what if you have a condition that will yield a vector of logical values? In that case, you should use this function, if-else function. So this is a specific function that you can use to deal with vectorized logical values. We will talk about it a little later. For now, just pay attention. The condition can only take a single logical value. And if you have more than one condition, for example, you have 2 conditions to evaluate at the same time, you can use some operators to combine them or connect them together. So in R, we use this double AND signs to connect to denote AND condition. So A and B is denoted in this way. A and B, okay, two AND operators. And for OR conditions, A or B, we use double bars. And both A and B will yield one logical value. So true and true, true or true, etc. Okay. So let's take a look at one example. X is 5, Y is 3. If X is greater than 0 and Y is less than 0, then Z is the sum of X and Y, else Z is the difference of X and Y. Okay. So you evaluate two conditions at the same time. Apparently, the first condition will yield a true. The first condition will yield a true, and the second condition will yield a false, right? True and false. So they together will yield a false. So Z is equal to X minus 1. So then you see, if you type Z, you get 2. Right? And in the following example, the OR condition, if one of them is true, then the whole thing will be true. So in this case, X is greater than 0, Y is so true or false will be true. Right? So W is equal to X plus Y. So W is equal to 8. So if you have more than one condition, you can use AND or operators to combine them together. And sometimes you have multiple lines of actions. In that case, you should use curly braces to wrap them together. For example, if X is greater than or equal to 0, we define two variables at the same time. Y is equal to X, Z is equal to negative X. Two lines in action 1. So wrap them in curly bracket or braces. Otherwise, Y is equal to negative X and Z is equal to X. So basically, Y is equal to the absolute value of X. Z is equal to the negative of absolute value of X. This definition. You define two variables at the same time. So it's possible, just don't forget to put them in a pair of curly braces. And if you have multiple conditions to check, a sequence of conditions to check, and they nest with each other, we need multiple if-else statements. For example, if you want to convert a score into a letter grade, we can use this sequence of if-else conditions. If X is greater than or equal to 90, then the letter grade is equal to A. Else, if X is greater than or equal to 80, B. So in each of the following else if part, we actually will exclude the previous cases. Okay, so this means greater than or equal to 80 and less than 90. Exclude the first condition, and etc. So by doing so, we can assign a letter grade based on the regular score. And lastly, the if-else function. If you have vectorized logical values or logical conditions to consider, you need to use the if-else function. So the syntax is this: if-else condition A, B. So how it works? If the condition is true, then the result should be A. Otherwise, if the condition is false, then the function will yield B. Right? And since the condition may be a vector of logical values, A and B are maybe logical vectors of values too. Okay, so really depends on the length of condition. If the condition will yield n values, then most likely A and B are of the same length, a vector of n values too. So, and it can be used to deal with single logical values, single conditions too. And for example, x is greater or equal to 0. So x is a single value, so this will yield a single logical value. It's okay. If it's positive, then y is equal to x. If it's negative, then y is equal to negative x. So this is essentially the same with what we did in the previous slides. Y is equal to the absolute value of x. So it can take a single condition. But it can also be used to deal with vectorized logical conditions. For example, x is equal to negative 5 to 5. So this is a vector of 11 values. And then you can put it in this. Okay, x is greater than 0. So this will yield a vector of 11 logical values. Right? And for individual values that are equal to true, then y is equal to x. Otherwise, equal to negative x. So it will do the comparison and evaluation element-wise. So this is the result. Okay. So previously, when we talked, so for example, if in the previous example, we tried to use an if-else statement to do the following, but we got an error message because the if statement, the condition part has to yield a single logical value. But you can safely put it in the if-else condition, if-else function. So you see, if x is less than 3, then take the square of it. Otherwise, keep it as the original value. Okay, so it's totally fine. So this is a special case. Of course, it's kind of like restricted because the two values, A and B, are in a very simple form or format. Right? And you cannot write like multiple lines of code for each action. Right? So it's restricted, but kind of convenient to use. Okay. All right. Yeah, this is another example. We generate 1,000 observations from standard normal, and then use the if-else function to check if a value is normal or not. Normal means it falls in this region from -3 to 3. Right? For standard normal, we know that about 99.7% of observations are in this region. If it is outside of it, we think it's abnormal. So this is a very fair definition of standard normal random variables, right? So if we do that, we save the result here. So y is a vector of 1,000 character string values, normal or abnormal. It depends on the value of x. And then we can use the table function to summarize the result of y. Turns out that out of 1,000 values we generated, 3 of them are abnormal. 997 of them are normal. They are within the normal range. And the last thing for conditions that yield multiple logical values, if you have more than one condition to evaluate, you use the single and or single or operators to connect them. Okay, so for single and, you use this A and B. For yeah, and for OR, you use bar, single bar. Okay. So it's kind of like not very intuitive. If you have single conditions that yield single values, single logical values, you should use double N or double bar to connect them. If you have vectorized logical conditions, you use single N and single bar to connect them. But it is just defined in this way. We can only follow the rules. All right, and another conditional statement in R is the which function. The which function will return the index of an observation. So it is useful for extracting observations or identifying observations meeting the condition. Okay, so it is used to extract rows from a data frame. For example, it will take a data frame and check each row, and if for each row, if the condition is true or not. If it's true, it will extract the index or the row index of that row. Okay, so it can be used to subset data. For example, we create this little data frame with five rows, 3 columns, ID, age, and sex of the individuals. And then suppose we want to subset observations of female individuals. We can do this. Take DF and extract the sex column and check if it's equal to female or not, F or not, and put it in the which function. So this will actually yield a vector of indexes where the condition is true. Consequently, we can put it in the position of the row index in the square bracket to subset observations of female individuals. Okay. Similarly, you can pull out observations with age that is less than or equal to 20. So this is a special conditional statement in R you can use. All right, so that's all for conditional flow. We talked about if, else, and if you need else if, you just use else if with a space in between. And we also talked about the if else function that can be used to deal with vectors of conditions. Okay. So now let's move on to the second topic, for loops. Okay. We will talk about 3 types of loops in R. The most commonly used one is the for loop. So let's take a look at an example and examine the syntax. X is a sequence of consecutive numbers between 0 and 10, actually even numbers. So X has 6 numbers. And we can write a for loop to calculate the square of X, each value in X, and print it out. Okay. So we first measure the length of X, save it in here in the variable N, then write a for loop. For I in 1 to N, parentheses, do something. Okay. So in this syntax, this I is called a looping variable. And 1 to N is a vector of values. Usually we use some consecutive numbers in it, with some consecutive numbers in it. Okay. So looping variable in a vector, a numeric vector. Okay. So this is whatever after the for keyword. And then parentheses, right? Write something in it, whatever you want to do in each iteration. By the way, I in 1 to N, that means I will start from 1, and then it will be 2, 3, 4 in each iteration. and then it will end at n. So that is the whole thing. And this part is the action you want to do within in each iteration. So it might contain multiple lines of code, but the looping variable I should be involved. Otherwise, the looping variable will not have any influence. It doesn't make sense, right? So there must be some expression that will involve I, the looping variable. So for example, in this example, y is equal to, in each iteration, y is equal to xi squared, and that will print y. So this is an example of a for loop. Notice that in this case, only the value of y in the last iteration will be saved in your workspace. For example, after you run this code, you type y again, y will be equal to 100. Only the last value is saved. A better operation, better practice is to create an empty vector first. So let y be numeric n. So this will create an empty numeric vector with n values, n cells. And then in the for loop, we will gradually fill each component of y. Then if you type y, you see all the values are reserved. So this is a better operation. So usually we will, better practice, we will create an empty container, then fill it so that the variable will be saved, all the values will be saved. Of course, you might notice that we actually can directly do this. Y is equal to x squared. We got the same thing. Okay, it seems that we are wasting time here, okay, because in R, everything is done element-wise. We definitely can do this using the vectorization property of R. Right? However, notice that it's not always possible to do this. Right? If you have a lot of complicated calculations within the iterations, and you cannot simply do this. Right? So loops are still useful. So this is the syntax of a for loop for index variable in a numeric vector and some action. And so this index variable is also called a loop variable or looping variable. And this n vec can be any numeric vector. Any vector, actually, doesn't have to be a numeric vector, I believe. And in is a keyword. Action is a grouped expression. All right. So in R, if we can avoid using loops, in explicit loops like for loop or a while loop or a repeat loop, if you can avoid using them, just don't use them because it's kind of slow in R, especially if you have like 10,000, a million iterations to run. R can be very slow. So if you can avoid it, then just avoid it. Just go ahead and using the vectorization property of R in R. So vectorization is an implicit loop, actually. It's still looping over the observations in each vector. It's still a loop, but it is an implicit loop and can be done more efficiently. We can compare the system time, the user time. If you use a for loop, use 0.39 seconds. If you use the vectorization property, use less time. However, as I said, sometimes we have to use a loop because we have to put multiple lines of code in each iteration. More complicated calculation to do, then we cannot use this vectorization problem. And then let's briefly take a look at the other two types of loops in R, while loops and repeat loops. So the syntax of a while loop is like this: while condition. So this condition will yield a true or false value. If it is true, then it will execute the action, the lines in this part. If it is false, the loop will be ended. Right? So it will run until the condition is false. So if you use a while loop, you need to make sure that the condition will eventually be false. Or you need to put something in the action part so that the condition can become false eventually. Otherwise, it will run forever. It will become a dead cycle. And repeat has no condition even. Okay, so it will repeat action forever until it encounters this keyword, this break keyword. So it's similar in Python. Whenever you see break, then the loop will be ended. It breaks out of the loop. And what is the relationship between for, while, and repeat? For is the least flexible. While is in the middle. Repeat is the most flexible, which means any for loop can be rewritten in a while loop, and a while loop can be rewritten in a repeat loop, usually, right? But not in the opposite direction. However, it is always recommended to use the most restrictive loop, which is the for loop. So for loop should be the first choice. If you can use a for loop, use a for loop. If you cannot use a for loop, use a while loop. So in this order. All right, now let's rewrite the for loop using a while loop and a repeat loop. So last time we calculate the square of each component in X and define it as a Y. So this is using a for loop. There is a looping variable, a numeric vector, action. If we want to use a while loop to do the same thing, we need to do the following. First, define the looping variable I is equal to 1. So this is called initialization. Initialize the value of I. And then while I is less than or equal to n is the length of x, predetermined. Then do the following, calculate yi is equal to xi squared. And then you need to update the looping variable I by yourself. So if you add 1 to the current value of I. So in each iteration, I is increased by 1. And you can imagine after the vector of y, all of the elements are filled, then I will be greater than the length of x, which is 6. When I is equal to 7, this condition will not be satisfied, will yield a false, and the while loop will be ended. So if you compare a while loop and a for loop, you will see that if we want to use a looping variable like I, you first need to initialize the value of it, and you need to update the value by yourself within the while loop. So if there is a looping variable you want to use, you better use a for loops directly. It's easier because in a for loop, it exactly knows where to start and where to end. You don't need to initialize it. You don't need to update it. But anyway, it's an option. And how about repeat? Same thing. If we want to duplicate this example, we need to initialize the looping variable I, and then repeat, calculate the square of xi, and that would be yi, and then manually update I, And then in addition to that, you need to add a condition so that eventually the loop will be ended. So in this case, we will check the index. If I is greater than n, then break. The repeat loop will be ended. So apparently, again, if you have a looping variable, you'd better just use the for loop. Okay, and repeat can be used to do something special, I guess. You repeatedly do the same thing, and until a certain condition is satisfied, and also the while loop similarly. Anyway, these are the three types of loops in R. It's better to know them. And some exercises, we'll skip them. Right? And then let's move on to functions. And we will first learn properties of functions in R, and then we will learn how to write a function by ourselves, self-defined functions. Okay. First introduction, everything which is done in R is done by functions, actually. So it has some inputs called arguments and an output called return value. So in R, you can only return a single object. Pay attention, not a single value, a single object. For example, you can return a vector as long as the values are wrapped in one object, like a vector or matrix or data frame is okay, but it must be one object. Okay. So let's take a look at, first take a look at the structure of a function. For example, the union function. Union is a function, we have learned this before, right? If you just type union without parentheses in our console, you'll see the structure of the function. The arguments, basic arguments required, and the action in the function. So it first will convert x to a vector, and then convert y to a vector, and concatenate them together and find the unique values of the two vectors and return it. Right. So this is the whole thing about the function. For the union function is very clear. Sometimes if you type the function name in our console, you might not be able to see everything. But for union, it's very easy. Right? And if you want to just check the arguments of a function, you can use the args function to pull out the arguments. For example, for union, there are only two arguments, x and y, right? And now means there are no default values for the two arguments, which means whenever you call this function, you have to specify both x and y. Right? You have to input the values of x and y. You cannot omit them, which makes sense, right? You want to calculate the union of two sets, you have to feed two sets. And how to use a function in general, so usually functions, arguments have their positions and you don't have to specify their names. For example, you want to find the union of these two sets A and B, you can just put union AB, it's okay. You can get the result correctly. You can also use argument names. So this is a more like formal way, x equals A, y equals B. And if you call the argument names, then you can switch the orders, right? For example, you can just do this. It's totally fine. For union, it doesn't matter because it is a symmetric operator. And next, default values. Other functions, for some functions, there are arguments with default values and there are arguments without default values. For example, the R-norm function is used to generate random numbers from normal distributions. by default, the mean is 0, standard deviation is 1. So by default, it will generate numbers from standard normal. So you don't have to specify mean and standard deviation. You just need to specify how many observations you need. Right? So this n is necessary because it does not have a default value. Right? However, if you use the ARGS function to pull out the arguments, you see that there are actually 3 arguments, n, mean, and SD. But these 2 have default values. If you want to, so definitely you can change them. You can generate random numbers from normal distributions with a different mean and a different standard deviation. It works. It will work. And then let's quickly talk about writing functions in R. Of course, as I said, our class is not our programming class. We will just learn something that is necessary for us to solve data science and machine learning problems. We will not write very lengthy R code to do simulation or optimization or do a research project. We will just learn some basic things. Again, for writing functions, same thing. We just learn some very basic things. At least we can understand other people's functions. We can also write a simple function by ourselves to avoid repetitions in our code. So in R, to write a function is very simple. You just need to name your function, right? And then call the function. The function is used to create a function. And then parentheses, list the arguments that are needed in your function. It might be just one argument, or you may have multiple arguments. It's very flexible, really depends on how many you need. And then use curly braces to wrap the code in your function, all of them. And this expression contains everything. For example, I want to create a function called square to calculate the square of the input. So I only require one input and will return x squared. So after I define the function square, I can immediately call it. You see, I call square and put 5 in it, I get the result. So self-defined functions can be defined and used right away. Just remember, when you quit your R or RStudio, the function won't be saved. Right? So that's why whenever you write your own function, you better put the code in the script and save it. And next time when you open R, you want to use a function again, you need to redefine it with the same code, but you need to redefine it. It will not be saved unless you save the workspace, which is not recommended. I don't recommend you to save your workspace because you don't want to put a lot of things in the workspace, and which will be confusing for yourself, actually. It's better to rerun your code and redefine your function next time you use it. All right, this is this part is about variables defined in the function. So just pay attention, any variable or quantity that are defined in a function do not exist outside of the function. So they are kind of like intermediate results. For example, in this function, I calculate the mean of a vector of values. So m is the length of x, and then I calculate sum of x divided by m. So this m is defined in the function, right? But it is just an intermediate result. And after I define it, and then if I type m in R console, I will get an error message because m does not exist outside of the function. Okay, just pay attention to that. Although it worked, I already run this code. This function has been defined, but m does not exist. This is another example. This is an example of a function with a conditional flow. So conditional flow and loops are building blocks of self-defined functions, apparently. For example, you can create a function to calculate the absolute value of anything, an object, x. So if x is less than 0, out equals negative x, else out equals x. So this out is basically the absolute value of x. So it will return the absolute value of x. I call it ABS2 because there is a built-in R function that is called ABS. Okay, so I don't want to override the original function with a different name, ABS2. Similarly, we can put a for loop in a function, in a self-defined function. So in this function, I'll calculate the factorial of a sequence of numbers. So not a sequence of numbers. It's a factorial of n. Whatever n is, it should be a positive integer. Yeah. So this is I use a for loop to calculate the cumulative product and then return it. Of course, my function is not perfect. It cannot take 0. We know that by default, 0 factorial is also equal 1. Is also equal to 1. It is a valid input and there is a valid output, but my function does not include that case. We definitely can make it better. For example, you can add an if-else statement in it to take care of the 0 case. You can also add an if statement to take care of invalid inputs, for example, negative n. But this is just a simple illustration. Sure. All right, that's all for writing functions. Any questions so far? Okay. And then let's talk about the apply family of functions. So this is a very special family of functions in R, which is very powerful, very useful, because they are essentially implicit loops. So they are quite efficient in dealing with large data sets or matrices or lists. They are loops, but more efficient and more effective. And today we'll talk about 4 or 5 functions in the family. Apply, sapply, and lapply, replicate, and tapply. Apply is used for matrices, so 2-dimensional arrays. So all the numbers are of the same, all the elements are of the same data type. Okay. And then sapply and lapply are used to deal with lists and vectors. So 1-dimensional objects. Apply is for 2-dimensional. Replicate is also used to deal with lists and vectors. And tapply is used to deal with data frames, tables. So data frames and matrices are still different, right? Data frames allow different data types in different columns. And matrices, and the elements should be of the same data. Right. All right, let's take a look at the apply function first. So it is used to apply a function paragraph. All right, let's take a look at this apply function. It's used to apply a function on every row or column in the matrix. So it has three basic arguments, X, D, and F, where X is the matrix or the data we have. And D is the dimension of X, which is used to specify a row or column. If D is equal to 1, then you will apply the function on to each row, on each row. If D is equal to 2, you apply the function on each column. It's used to define the dimension. And F is the function. For example, I define a matrix A, a very simple matrix. And then if I want to calculate the row means, then we can just say apply A1 mean. 1 means along the rows. So calculate the row mean, right? So the function is mean. Right? So the last one, the F part must be an existing function, either a built-in R function or a function you just created. Okay? It should exist in the workspace already, right? And so now we apply the mean function on each row. So we have 4, 5, 6. Very simple, right? And similarly, if you want to calculate column means, then just change the dimension D to 2. Then you will calculate the column means, which are 2, 5, and 8. So this is applied. Very simple, right? And then let's move on to the second group, S apply and L apply. So they are used to apply a function on every entry of a list, every component of a list or vector. So the basic syntax is L apply X F. X is the list, F is the function. Since lists and vectors are one-dimensional, you don't need to specify the dimension anymore. It's only one-dimensional. You just apply the function on each component. For example, let's see the following example. So n is a vector with 3 numbers, 5, 10, and 20. Then we call the lapply function on n, and the function we apply is rnorm. So then it essentially means we apply the rnorm function on each value of n. So we'll first do this, and then rnorm 10, and then rnorm 20. And the result is a list. We call it out. Out is a list. If you print out, you see the first component of out is a vector of 5 numbers, 5 standard normal numbers. And then second is rnorm 10, the result of rnorm 10, so 10 normal random variables, then 20. So see, it takes a list and return a list. Apparently it's a list. So first component, second component, and third component. And we can also apply the mean function on each component of out. Because out is a list, right? We can apply the lapply function on out again. Apply mean to each component of out. Then we have a list again. Right? The mean of these 5 numbers is this. Mean of these 10 numbers is this. Right? This is lapply. Right? The result is a list. Sometimes we don't like the format of lists because they are kind of not very neat and convenient to use. We can choose to unlist the result, use the unlist command to return the result into a vector. It's possible to do that. However, R has this sapply function, which essentially combines the two things. It will call the lapply function and at the same time unlist the result into a vector. So for example, instead of using lapply, so we can use the sapply function and on out and calculate the mean of each component of out. So then you see the result is a vector instead of a list. The values are the same. but it's in a more convenient format, which is a vector. So that's why we talk about these at the same time. They are similar functions. But notice that it's not always good to use the as apply, because you see this one, you'd better not to use the as apply, because the three components have different shapes. Right? And you might want to use the three components in different ways in a little later, so you'd better not put them in one single vector. And the next function is replicate. So this function is a little bit similar to the repeat function we just talked about. It will just repeat the same thing again. But this replicate function is within the apply family, so it's an implicit loop. It's more efficient, quicker to do any operation. For example, and the result is also a list. For example, I want to generate 10 samples of standard normal random numbers. And in each sample, there should be 100 observations. Then we can just do this replicate 10 R norm 100. So this will generate a list of 10 sets of standard normal random variables, and each set has 100 observations. The result is also a list. We saved it here. And simplify equals false will save the result into a list instead of a vector, right? Because I want to keep the result as a list instead of a vector. And then I apply the as apply function to out and calculate the standard deviation of each set. So then I have this vector of standard deviations of the 10 sets of standard normal random variables. So anyway, this replicate, it can be used to do one operation multiple times. If you don't want to, you don't need to change anything in each iteration, you can just use replicate. And last one is t-apply. T-apply is used to manage tables. That's why it starts with T. So it can be used to evaluate a function on data in a vector or list, which are grouped according to the levels of some other factors. So it's a way to summarize numeric variables that are grouped by some categorical variables. For example, let's use this genotype data set in the mass package. So the mass package is a built-in package in R. However, you have to load it before you use it. So it is available for us, but you have to load the package. It's not available for you before loading. So let's load the package, and then this data set is available for us. Let's take a look at a few rows of it. Notice that I use a sample function to sample five indexes, row indexes randomly, so that we can see some variation in the 5 rows. Otherwise, it will show if you use a head function, you will only see the top 6 rows. And because the data are ordered, so you will see a lot of repeated values in leader and mother, etc. If you want to see a variation in the rows, then you can do this. So there are 3 variables: litter, mother, and weight. So let's see the data. So this contains data from a foster feeding experiment with rat mothers and litters of 4 different genotypes, A, B, I, and J. And in the experiment, rat litters were separated from their natural mothers at birth and given to foster mothers to rear. So it's kind of a random design. So after the mothers gave birth, we will switch some of the letters to different mothers. So for example, in the 32 row to 32nd row, the letter B, mother is J. So this is a foster mother. This letter B, this is the true mother. So they belong to mother B. Actually, they were delivered to mother J. And then weight, this is the average weight of the litter of those rats. Suppose you want to calculate the average weight for each litter. Right? We first attach the data set. So a data set is available for us, but if you want to use or call a vector or a column of the data frame, you have to use this kind of expression, general type, $, for example, weight. If you want to call a vector, you have to do this. To avoid doing this, and in this part of your workspace or code, you only focus on this one data frame, you can attach the data set. If you attach the data set, then all of the columns are available to you to be used directly. So after I attached it, I can call the columns directly. So now we want to calculate the mean rat weight in each litter. Okay. Oh, sorry. So this weight is not average weight. This is individual weight, the weight of each rat, baby rat. So we do this. So first is the vector of interest, the numeric vector. We want to count the mean weight. And the second variable is the grouping variable. We group the rats by litter. And last one is the function. We want to apply weight. If you run this, you see we can calculate the mean weight for each litter. If you want to calculate some more statistics for weight for each litter, you can call the summary function. As we have learned before, summary function will return the 5-number summary and the mean of a numeric vector. And do this. Still use the t-apply function. And you can also use more than one categorical variable to group your numeric variable. For example, we can calculate the mean weight of rats in each combination of litter and mother categories. Just remember, you need to use the list function to wrap them together, which means you're considering all of the combinations of litter and mother. So totally 16 of them for categories of litter, for categories of mother. So 16 unique combinations. And then within each small group, you calculate the mean weight. So this is possible using the t-apply function. You can add more, but then you would create like higher dimensional arrays, which is not convenient actually. So maybe up to 2. Okay. All right, great. We still have 15 minutes. Let's talk about best practices in coding. As I said, these are kind of general recommendations for all coding languages. So in general, these are the principles. Plan your approach, use indentations, make use of comment lines, simplification of code, consistent naming scheme, coding groups, and effective debugging. So let's take a look at them one by one. first plan your approach. Before you even start coding, you need to carefully plan your code, your program. Right? So figure out the direction and plan your course of action. Okay, carefully examine your research question and what data you want to use and what goal you want to achieve, etc. And write down the approach on paper. So before you code, it's better to write down the main steps in your code and then dissect the big problem to smaller parts. This is also very important. It's better to start from the bottom and then build them up to a big program. I focus on, so dissect the big problem to smaller problems and focus on each part. Dwell on specifics. Sometimes your program may have an error or something that is very difficult to debug. That's because you probably ignore or neglect something that is very specific. So dwell on the specifics, very important too. And the second principle is using indentations. In R, it's not required to use indentations. For example, if you write a for loop or an if-else statement, you don't need to use indentations. However, it's highly recommended to use indentations by yourself. Right? For example, in this nested for loop, I intentionally add indentations to clearly mark different layers of the for loop. So this is a nested loop with 2 layers, right? So this is the inner loop, and this outer loop. And within the inner loop, so this is the action in Python is required, but in R is not. But I suggest you to use indentation whenever you can. You should. And then make use of comment lines. This is also very important. No matter how familiar you are with your current program or code, later on, after a few days, you will forget. You need to write some comment to remind yourself the purpose of each line, not each line, important lines, or confusing parts. So, and also it's helpful to communicate with your teammates and also report to your boss in the future. And lastly, avoid obvious comments. Don't put unnecessary comments. Like for example, you define a variable x equals 5. And you say, oh, define a variable x, which is equal to 5. So this is totally unnecessary. And then next part is simplification of code. First, the DRY principle. DRY stands for don't repeat yourself. So whenever you notice that you will repeat a part of your code, try to use loops to avoid repetitions, or write a function. And next time, whenever you need to repeat this part, just call the function. Okay, so this is very important. Don't repeat yourself. Next, limit line length. So our eyes are more comfortable when reading tall and narrow columns of text. So we're good at reading something like this instead of reading something like this. In coding, also we should write long and narrow blocks of code instead of wide, very wide code. And sometimes you even need to wrap it to the next line. So that is not a good practice. I try to avoid writing very wide rows of code. And next one is avoid deep nesting. So for example, this is a pseudo example of a very deep if else statement. Right? So this is not good because it's really difficult to understand and really easy to make mistakes. Try to avoid this. And next one, consistent naming scheme. So for beginners, sometimes we don't pay attention to how we name variables. But in the long run, it's always a good habit to name your variables in a very consistent way. So first, when you name a variable, you should use word boundaries in names. So there are two popular options to separate your names, the names in the name of variable. Separate words in the name variable. For example, the first one is camel case. So the first letter of each word is capitalized except for the first word. For example, the variable is called first year income. Then this is an example of camel case. The first letter of each word is capitalized. Each word is capitalized except for the first one. But of course, you can also capitalize the first word. It doesn't matter. I usually capitalize the first word as well, okay, to make them look more consistent, okay? But you don't have to. And the second choice is using underscores to separate them. First underscore year underscore income. Okay? So this is also a very good way. Don't use period. Use period. Yeah, sometimes people use period, but it's not recommended. Next, using meaningful names for variables and functions. Consider two variables, first year income and FYI. Okay. So FYI is short and simple. However, it is meaningless for you and for your readers, although it's very short. So it's better to write relatively long but meaningful variable names instead of using these meaningless variable names. Okay? Because in the long run, you need to go back and use your code again or modify your code. It's better to make everything very straightforward, very clear, easy to understand. And next one, consistent temporary names. So, for example, temporary names are used in loops or in functions, etc. So if you use I for the outer loop, then you should use something like J or K in the inner loops instead of using X, Y, Z, etc. So just to follow some kind of convention is good, be consistent. And next, code groups. So this is also very important. Whenever you have very long program or code, you always should separate your code into blocks, coding blocks or groups, and clearly label each part. Of course, if you use R Markdown, it's very convenient. You can just separate them into different short code chunks. For beginners, beginners tend to put a lot of code in one code chunk and try to run all of them at the same time. This is definitely a bad practice. Okay? Instead, you should separate your long code into smaller code chunks and run each part separately. Okay? So it's much easier to debug in this way. If you put everything in one code chunk, it's very difficult to debug. You don't know where the error is from. And the next one, debugging. So this is also a very common problem for beginners. Especially in R, the error message is not very easy to understand sometimes. Okay. So how to debug? So first, read the error message carefully and think. You need to just calm down and think about it. Maybe the error message is very clear. Okay? You can easily debug your code. Okay? And then if you cannot figure it out, scan a few lines above and below the line with the error. Okay? Sometimes it seems that R told you that, okay, line 36 has an error. But actually the error is right before it, okay? The cause is above that row, okay? 1 or 2 rows above that. So scan a few lines above and below the current line. Okay? That is indicated to be wrong. And then if you still cannot figure it out, okay, you can Google search. Just carefully copy the entire error message and put it in the Google search bar and hit enter. Okay. So usually in the first page, you will see something that is very related because trust me, a lot of people have the same error. And of course, it requires some patience and time. You need to read the posting carefully, and a lot of people will answer the question, but not all of them are useful. Identify those useful solutions and try them one by one. So that is another way. And again, dissect big chunks to smaller ones. So if you really cannot debug, then check the code line by line. Okay. Run the first 3 rows, no bug. Okay. Add 1 row, no bug, etc. And then essentially you should be able to find the part with error. Okay. And then check in intermediate results. So sometimes you choose not to show unnecessary intermediate results, but clues may hidden. Yeah. So that is also a very important point. Okay. Sometimes because you only need the final result. However, the intermediate result can show you what is wrong. Okay. So in this case, for example, you write a function with several intermediate results in it, and the final result is wrong. Although it runs, the function works, but still the result is not what you expect to see. In that case, you can get rid of the function, break the function, and run each chunk in your function one by one and check the intermediate result. If, for example, it will return y eventually, okay, but in the middle of your function, in the function, you have some intermediate result, x1, x2, etc. Okay. So in that case, you can just choose to print x1, print x2, okay? And then check if x1 value is what you expect to see, x2 is what you expect to see, etc. Okay, until at the end, you return y. Right? So this is a way to debug your code too. And if you still cannot figure out what's wrong, then you need to go back to your very first step and review your plan and see if there is any intrinsic mistake. Sometimes the plan is wrong. At the beginning, remember you write everything on a piece of paper. Okay, for example, you want to write a function to solve an optimization problem, some problem, and then suddenly, when you review your plan, you see that okay, one formula is wrong actually. Okay, the formula is something is missing. Okay, then add it. If your original plan is wrong, definitely your code will not work in the same way that you want to see. Okay. So that is the last one. All right, so these are some common practices. I hope if you are a beginner in R programming, I hope you try the best to follow these guidelines. So then you can improve very quickly. Right? Just don't intentionally to ignore any of them. Try to start with very good habits. Start programming with using very good practices. That will be very helpful. All right, that's all for today. Any questions? Any questions? No. Great. Then tomorrow we will start to talk about data visualization. We'll first talk about the concepts, theories about data visualization using R and R packages. And then we will talk about how to use ggplot2 to create visualizations. Okay. All right. See you guys tomorrow.